Thanks for joining me right after lunch. I'm Marcel. I joined Clyso a couple of months ago to work on Ceph. And this one is about understanding Ceph one performance counter at a time. And what does that mean? This is a bit of my learning journey. I set out to see what can we learn of how Ceph works by just looking at those performance counters, not at logs, not at tracing, but those counters. So to scope this talk a bit, we are looking at performance counters, and it's about developing an intuition, how to find them, what they mean on their own. And I went ahead to find this out with a series of experiments, on which I'm going to show two. There's a couple of more. At the end of the talk, I'm going to share a link to a GitHub repository. There's this notebook file in there, which has a couple of more, and also commands for JQ and to parse stuff, things like that. And we are looking at raw performance counters. And with raw, I mean, it's not going through Prometheus, Grafana, whatever. It's getting them directly from the daemon. And the talk is structured in roughly 3 parts. At first, I'm going to introduce performance counters. What the types do they have? What makes them special in the Ceph context? Then we look into counters, one of those types, and then we look into how to look into latency. All right, what is a perf counter anyway? I looked up a definition, and that says a metric is a measurement of a service captured at runtime. And the first thing to note is that what Ceph calls perf counters or performance counters is in other contexts called metrics, usually. For me, it means the same thing. I don't really know where the perf counter comes from, this name. I think the hardware people call it that, for example. My personal definition is a bit different. It's values captured at strategic places. And what's in there is that as a software engineer, performance counters are sometimes kind of table of contents to a module. If you look at code and you find a file and it has all the definitions to perf counters, they usually point to interesting places. For example, if you see a performance counter that records the latency of an operation, if you go to a reference to that, you will find the end of the operation processing. And that's sometimes great to look at. And to give you some example of what performance counters do, for example, if librators sends the write operation, so you increment the OSD op write counter. And, I don't know, if you process an operation to record the latency. So let's see what types of perf counters we have. There's the gauge. The gauge is like a pressure gauge, fill level in a beaker. It's a value you can measure. It has I don't know, a weight. Or in the Ceph context, it's how much space is available on an OSD. Or the ones that I love to look at, how much stuff is in a queue or is waiting to be processed. Then there is counters. Counter a value that increments all the time, except that they sometimes tend to go through 0. For example, you restart a service, or I don't know, uint64 overflows. That doesn't happen too often, I guess. Then there's a bit more involved types. There's the histogram and the long-running average. So the histogram is a bit like a counter, but you have buckets. For example, here you see buckets for 1 to 3 milliseconds, things like that. And every time an event occurs, imagine an if statement. Fits in this bucket, increments that counter. And that gives you a distribution of things that happen in a certain size. They're a bit rare in the Ceph context. You will way more often find the long-running average. And if you look at this chart here, the long-running average, it's this green bar here. With every observation, which is one of those bars in the bar chart, you push or pull this average to some place, right? And in the Ceph, they are implemented, for example, not really as this one value. They are rather a count of how many observations and then a sum of all of them. If you would flip all those bars in the bar chart and put them together, you would get that sum. And How to read perf counters? I've said raw perf counters. This is like the typical commands you run. You get them from the admin socket. The first one, for example, for RGW, you need access to that file, and then you run perf dump. There's also perf schema, which tells you like a description of the thing and its importance set by the developers. There's also a bit of newer commands called counter dumps. They are about like labeled perf counters. We won't really look into them here, but they exist. So what do we get back? Yeah. We get enough JSON to fill a slide at 2.6 point or like 17K in computer units. The nice thing with what you get back from perf dump is it's like not a deeply nested JSON. It's like group name, key, value. So it lends itself to like ad hoc parsing on the command line actually. And like how many perf counters are there? I wanted to ask me this question, and I don't know, threw together this weird web app that extracted all the schemas and tried to put them together. And what I saw was like, okay, there are quite a lot. Scroll. I still have no idea if this tool is useful. Yeah, if anybody finds it useful, please tell me. What I found is on my like vstart cluster from Ceph main of last week, you get around 880 counters and roughly like 41 groups. And with groups, I mean there are sometimes duplicated entries. And for example, the messenger exports 3 times this like data that looks the same, but is actually each thread. So that would be one group, and what I mean with groups. So we won't look into 880 counters. No time for that. We will focus on these 3 groups. The objector, that's part of liberators. It can tell us things like what kind of operations happened and what were their latency. There is the async messenger. This tells us what went out of the network and went back. And we look briefly at the OSD side. What can we learn there? All right. So let's look into counters or counting things. And for that, I used a very simple example. We look into a single 4 megabyte S3 put. I mean, yeah. And this above here on the slide is like everybody familiar to RGW knows this is the output. So whenever working with performance counters, it's a good idea to test your assumptions. Did that event really happen? Does it make sense what I'm seeing here? And this one already contains 2 metrics. Yeah, it gives you the size and it gives you the latency. And there's like a hidden metric in there, the 200 there, it means success or failure. I think that's also tracked by RGW. And if you perf dump an RGW, you find that you get this information again as perf counters. There's a counter that's called RGW rec. This one increments by 1. It increments for each request. And there is special counters that count like put operations, for example. But this is not the ones that I wanted to look at. The ones that are more interesting are the things that tell me what went out to radars. And I know it's like a long list, so let's filter out all the zeros and look at what went over the wire via liberators when you do a 4 megabyte put. So there's 18 operations reported, and you see here there is like the one that probably not everybody expected is the write full. This 4 megabyte user data need to be somewhere, and there is other operations like set etc. And this one sets for on Rados objects extended attributes, which is also not terribly surprising that you see them because S3 is a rather metadata-heavy protocol. And the operations that I find most interesting are the calls. So the calls are object class calls, that is code that lives on the OSD and is especially there for like those complicated special operations that RGW needs. Example is, for example, updating the bucket index. The thing is, it's all meshed together in call. So to get like drill down further, we can't really use metrics. This would be a territory of tracing those things to find like what is the arguments to those calls. But still interesting. We got 18 operations. So let's look one layer down into the messenger. Here we'll see a bit of a surprise because the messenger sent out 3 messages and we just had 18 operations. That's a bit weird. But we can also find out how much bytes went out and in. So we can actually even compute like what is the overhead of this operation on the side, on the Rados side. Okay. So let's put like these numbers on one slide. If we sum up the OSD ops and the OMAP ops we saw, we get 18. Messenger saw 3, and there's another counter, objector.op, also reported 3. So what does this mean? Well, actually, to look at the code for that, so they track different things, kind of. So an operation on that level can actually be a list of multiple operations. And they are like used to like batch up things, but you can also build Rados, you can combine Rados operations into like more interesting ones. For example, you can use a version assertion and a write to build some kind of conditional write, where the second operation will only go through if the first one succeeds. So what we see here is that those 18 modification reads that we see through Rados are actually packaged in 3. You can also look at the overhead. For my machine, it was around 4K. And we can look at the OSD side of things. The OSD side of things, my setup, 3 OSDs. And that side again tracks our operations. What we can see here is that Ceph divides those operations between between every OSD. And we can also see where those data went. It, of course, went only into one. But there's also counters that tells us how the replication, like what was replicated. Those are hidden in the sub-op counter. So for example, what we see here, OSD2 received the 4 megabytes, and then the others received the same 4 megabytes through the sub-op. Okay. Let me summarize. What does this actually teach us? Yeah. So looking at those counters individually for a single experiment, it tells us what is the mix of operations we have on the cluster. Again, in practice, we wouldn't really reset clusters and do an operations and see the raw counters. We would take the derivative and get the rates of operations. We wouldn't use pie charts. We would use like stacked bar charts to see what is the mix of operations we see. We also learned that the single Rados operations, they batch up into bigger operations that went over the wire. And we could see that it takes 18 different things to do for an S3 put to go through in Rados Gateway. Okay. So let's look into how we can understand latency in the system. And for that, we look at a couple of different ways to measure those. So at first, this one is a different workload. This one is like I ran an S3 benchmark, which has an operation mix that you see on the left side. Mostly gets a bit of puts, a bit of deletes, and a bit of stats. Stats are basically those head requests. And these turn into that like other pie chart. And we can see again, RGW is heavy on those calls. We can also see that there's a bit of write fools, a bit of reads, a bit of stats. So this is our operation mix and how to understand the next numbers we look at. So what numbers can we look at? The client side, again, tracks for us the op latency. In my case, it was an average of 43 milliseconds. This all ran like on a laptop, and so don't take those numbers into any like comparison to something real world. It's just there so that we have numbers. And on the OSD side, there's another counter, the op latency one, that we can look at. In this case, we get 3 values, 3 OSDs, 3 values. We get another set, like 41 milliseconds to 39 milliseconds. All right. We got around 40 milliseconds average latency. So is that actually like meaningful to us? Like what can we like learn from that? So, I know, dramatic. The thing is, this is only like you can only understand this number if you use it in context of the operation mix that is happening on the cluster. Like imagine this number goes up on your cluster and you're like, okay, what happens? Is it like a hard disk going slower? Or maybe it's just the backup job that changes our operation mix to more writes, because like usually writes take longer than reads, right? So how can we better understand these latency numbers? And for that, the nice thing is that op latency, this metric, is actually a family of metrics. So there are separate ones for writes, for read writes, and for reads. And if we look at them, we get values that are like, we had around 40 milliseconds before, but we see now that reads are actually way faster than that, and writes are actually way slower than that. And so this like teaches already a bit more about how to understand our workload. But still, if we think of this pie chart, there were the writes, and those writes tend to be big. There were those calls, and they tend to be small, right? So, and the OSD doesn't really handle them the same way necessarily. Right? And so, can we like drill down further than that? And it turns out we can. So there is histograms we can look at. There is actually 4. So I meshed them together here in this bar chart to look at them. And this one is like interesting because if we now look at the reads are this lighter color greenish thing. And we can now see that they actually have like 2 maxes in their distribution roughly. So there's reads that take under 400 microseconds. And there's reads that take up to 50 milliseconds. And they were all before. This were all in this 41 milliseconds average. This is all in there. But this is drilled down a bit more. And so we can see that there's reads that are vastly faster than other reads. And we can see that writes are also not all the same, made all the same. So histograms they're like a great way to understand more what is going on. And so here's like a summary of what kind of histograms to look at. There's 4 on the OSD to look at, where op latency captures everything. They capture, like there's one that captures reads, there's one that captures writes, and then there's 2 that captures read writes. And there are separate ones because one looks at in bytes and one looks at out bytes. And people knowing Ceph would maybe like twitch a bit because aren't like histograms in Ceph like 2-dimensional, a bit different than that? And yeah, they are not 1-dimensional as I showed them before. There's another dimension to them, and it's written here with the data. They're also a bit hard to put on slides, because if you look here at this table thing, the y-axis is our latency buckets, and the x-axis is the size bucket. So let me add some color to this thing. So what we can learn with this actually is that that our reads, for example, on the left side, the reads, we have like this hotspot around 200 to 400 micros, and they tend to be in the same size. They're roughly under 1 kilobyte. But this is not all. This whole column is means that we have operations that are roughly the same size but take vastly different time. For example, there is a couple of operations that take up to 100 milliseconds. And this is, of course, like interesting to drill down further, but we need different tools and metrics for this. This is like territory usually of tracing or like some systems. Not sure if Ceph has on like slow logs that only logs those entries that like fall out of the distribution. We can also see that on the right-hand side that there's other reads that batch up around in this 4 megabyte, 8 megabyte bucket. And this is like the typical data read, because Ceph objects are usually 4 megabyte in size. So that's the objects, that must be the object data we can see here. They are a bit closer together latency-wise. So there is something odd happening, I guess, with the smaller stuff that is usually hidden in those calls. To make this a bit more clear, we can like invert the color scheme a bit and see only the outliers. So this is great to do a bit outlier analysis. I still have like for me as like still a curious thing I would love to try is to have a histogram that is keyed by the operation rather than the size of it. Would be curious if like my assumption that left side in this chart is mostly calls and there are some that take a longer while are actually calls, or if there's something else going on there. All right, time for recap. So I went through 2 perf counter examples. The first one where we counted things. This is a great way to teach us like what is our operation mix. It's also great, like for example, as a developer to test assumption. For example, in an integration test, where you run a thing and afterwards want to see, okay, I think write should go out with Rados. If you, for example, build a cache or something, you can easily test that with just checking for a perf counter and seeing it's okay. This is bigger than 0. In the second part, we looked at latency and how far we can drill down from just getting an average latency, and we went down to seeing that we can understand latency in a histogram with the size and with latency buckets. So this was like part of my journey so far with perf counters. I also have like a bit of other stuff for like if anybody's interested to look in those things. Tracing is a great way to mix with that. There's Ceph supports trace points here and there to, for example, trace librators. There's a cool feature in the OSD called perf queries that you need a manager module for. But if you activate that thing, it can give you like a top 10 of the clients and their individual I/O. And so personally, I also want to drill down further to BlueStore, but I found that looking at those metrics, you kind of need to know BlueStore, and it's mostly latency focused, those metrics. Also, like, have a side quest of building a thing to do like a top-like tool for network connections and stuff that I'm working on. And with that, that's thank you for listening. This above here is a link to slides and a couple of tools. As I said, there's a workload notebook thing where with all the commands. Yeah, that's it for me. Thanks. And I think there's time for questions, like 10 minutes or so. Or, I don't know, tell me your favorite perf counter, or...
What's your favorite perf counter?
I really like the histograms on the OSD. That's probably my favorite. What's yours?
Did you use them for any
Not so much yet. I'm more the software engineer, unfortunately, to look at those a lot. I will. Yeah?
Yeah, I had some fun with, I guess, the counters, because there is one package called the disk preceptor or something like that to figure out if the disk is failing and so on. And I don't know if it's still in development, because there is an external company that ran it, and I read that ran it for a while, but it doesn't seem to have any updates, and it doesn't really work that well now. Are you looking into that, or have any experience with it?
To summarize, you ask about the disk predictor module. I don't have any experience with that. I heard it exists, and it does I don't know. Does it check smart values? Do you know?
Yeah, it checks a bunch of different performance counters, smart values, and so on, and trying to predict when the hard drive will fail.
Uh-huh.
It will give you a score if it's good, medium, or bad, so you can say, okay, in 6 weeks you need to change this hard drive.
Okay.
It's using an AI model, and I don't think it has been updated in a long while.
Mm-hmm. Does anybody happen to know about the disk predictor module? Okay.
So the only thing is I would love to have it working as well.
Okay.
How many of these counters are available in exporters? Because it will be nice to visualize it in Grafana
Mm-hmm.
and collect this information from some longer time. But I'm sure that some of this information are an exporter, but I'm not sure about others.
Mm-hmm. To repeat that, how many are exported to systems like Prometheus, Grafana? So how most of these values end up in a system like Grafana is they take the step over the manager, right? And the manager doesn't receive everything, every counter there is. There is actually I think it's called a priority feature. I think it only sends the important ones. I think that's how the value is called over. So not everything ends up there. That's why I looked at them from the daemon itself. I don't know. Does anybody know? Is there an exporter that directly converts the admin socket perf dump? I think there is, right?
Ceph exporter is normally the responsible of taking the perf counters from daemons
Mm-hmm.
and exporting them externally. It used to be the manager, but because of some performance issues,
Okay.
it took out the metrics from the manager, and now the Ceph exporter is the responsible.
Okay. Well, yeah, there is Ceph exporter that does that. Okay. Yeah? Yeah?
We're from DigitalOcean. We manage Ceph exporter. It doesn't
Oh.
do the admin socket perf stats. We have an internal tool that does that we talked about at this con. Well, we talked together about it. That it seems like it's very interesting to other folks to get some of these stats out of. We have a tool that does that internally. We might look at trying to open source that. It seems like it might be popular.
Uh-huh. Okay, cool. There is a tool, apparently. But when it doesn't do admin sockets, how does it get the data? It does do, okay.
Yeah, so Ceph exporter is the public one that doesn't do admin sockets today. Our internal one does.
Okay, you got one. Cool. Does it do histograms?
Yeah, we have the histogram graphs. Yeah, the Rails gateway.
Yeah, because for Prometheus you need to flatten them, right? Okay, cool. Yeah.
Any recommendations around tracing?
Recommendations around tracing.
Do you use for tracing, Jaeger tracing?
I tend to not use Jaeger tracing much because it's it's a distributed thing to look at more than one thing at a time, yeah. And what I tend to use is there is LTTNG trace points in Ceph that are compatible with things like BPF trace. Yeah, but you have to. I'm not sure those points are actually enabled with every Ceph build. I don't know. But I tend to run those, like, I tend to build my Ceph my own, so I'm a bit detached there, afraid. Yeah. Okay. Oh yeah, yeah.
What would you look at for looking at I/O amplification from maybe only the I/O at the top versus the amount of I/O you actually see on the back-end disk? So I'm looking for a kind of complete stack. So I want to see for each I/O I do here, how many I/Os am I doing right at the very bottom underneath the OSD?
Yeah. So I'm maybe 70% sure here. I think there are no stats for the disk in the OSD for like right before it hits the disk. I think that is considered like out of the system boundary. So you would have to combine that with something like a node exporter, and I don't know, do the label matching thing and compare that. Right? I mean, you need different sources in your system because, for example, the network is also not really captured. You get like the edges only. Does that answer your question, roughly?
Yes, that does. Thank you.
Great. So anybody else? It's a bit hard to see from here. Oh yeah.
Pretty basic question. I sort of understand what a read operation is and what a write operation is. What's a read-write operation?
Yeah, those are operations. I mean, as funny as it sounds, it's operations that contain both. If you remember the beginning of the talk, I said that there's 18 and there tend to be just 3. And you can combine like reads and writes into the package and them up in the combined operations. And if you have that, you have a read-write. So this read and read-write is basically a flag on the total operation that tells you what it does. Hope that answers your question. I don't see anybody else. Oh, thank you.